Okay, good morning. If you're just coming in, settle down quickly. We'll get going in 30 seconds or so. Okay, good. Well, welcome back. Week 4, lecture 7 in this course already. It's going quick. And as usual, I'm going to start by pointing out some of the new stuff that's been added onto Blackboard for you. So, again, in starting off at the base page, if you go to week 4, you can see the asynchronous reading, so the reading that you do ahead of the class. We've got a little bit from carryover from last week, rigid body motion, which is what we're going to cover today. And then also, what we're going to cover on Friday and next week is the introduction to control volumes and integral laws applied to fluid mechanics, which means conservation of mass, conservation of momentum. And that will take you through to things like Bernoulli's equation, which you're going to do in part 2. So there's an asynchronous video introducing some of the concepts of integral analysis, which I've put there in advance for you to have a look through. We'll go through most of the content on Friday, but it's there just for you to have a little look in advance if you have time. Yep, as of the last couple of weeks, we'll have a drop-in session on Zoom tomorrow, 11 o'clock. Everyone's welcome to ask questions. These are the slides from today. And there's a quiz. Yeah. A couple of people are starting to ask about practice questions. We will have some past exam papers in the next 2 or 3 weeks. You always have to be a bit careful with past exam papers because you know, obviously we've been teaching fluid mechanics for years and years and years, but the syllabus has been changing a little bit. So when you go through them, we have to point out the things that are still relevant and the things that aren't. In the meantime, if you kind of want a general purpose practice, Shaum's outline, which is the second core text, which is linkable from here, has got really quite a lot of good quality practice questions. It follows very much the same content and syllabus as the Frank White textbook. You'll see a lot of the same types of figures, slightly redrawn, same kind of analysis, so it should be familiar. It's perhaps a little bit more condensed. It's supposed to be like a revision guide, so some people find that a bit more digestible. You know, you see all these same types of figures that we've looked at, atmosphere, etc. But there's a lot of worked examples, right? So this is one is very similar to the one in the Frank White book that I set you to have a look at last week. And if you go to the end of each chapter, there's even more. So there's solved problems, then there's multiple choice problems, supplementary problems, and then I think there's usually like a practice exam as well. Loads and loads of practice questions. And if you're looking for more, definitely take a look at that section of the Shaum's outline. Definitely recommend it. Okie dokie. So, seems to be working. Okay. Right, so what's on the agenda for this week? Well, we've got on the synchronous side, today's lecture and Thursday's lecture, and the face-to-face tomorrow, and a tutorial this week. Same arrangements as last time, Friday 5 till 6 p.m, same groups, all in this building. And you're going to go through tutorial sheet 2, which is on Blackboard since last week. I've covered most of the asynchronous stuff, except that I'm going to post a video of the practice question at the end of last week's lecture, which was is going to be quite similar to your coursework, and then a practice question from the end of today's lecture as well. Again, these are questions that they're work examples from the Frank White book, and all I'm doing in the video is talking through it, explaining a little bit, linking to what we've done in class, so hopefully it makes it a bit easier to follow. And yeah, by the end of the week, you'll be issued with the coursework. Either be Thursday afternoon or Friday morning. You'll have 2 weeks, or just over, to finish that. Okay. I guess just a quick clarification on the quiz. A couple of people asked me again. The quizzes are running every week for the 10 weeks that we have lectures. So next week, but not week 6, because we have a lecture break then. And all of the quizzes are open until the end of the semester. So they're all open for you to try as many times as you like until the 17th of December. Log the highest mark that you can. And if in total you get over 80% across all 10 quizzes, you get your 5%. Okay, so today's lecture, we're going to be looking, if you like, our final special case of hydrostatics. Last week we were looking at manometers, measuring devices, and forces on immersed surfaces. This week we look at a slightly different scenario in hydrostatics, which are important to be aware of for the purposes of making assumptions. They generally are quite, they generally appear in real life in the form of assumptions. So there generally is an assumption that they will relate to, that you will be aware of, and we'll go through a few examples in today's lecture. So there's basically these two types. So you've got, last week we were looking at hydrostatics, stratified flows, forces on immersed surfaces, and pressure measurements. And this week, it remains, well, today only, it remains for us to look at rigid body motion. Then we complete the topic of hydrostatics. Now, hydrostatics, as is self-evident in the name, applies to the state when a fluid is at rest. It doesn't necessarily need to be water, as is implied by hydro. It is basically any fluid which is at rest and which is at a constant density. Effectively, in that particular case, we say that it's stationary, and the only acceleration that is acting on it is gravity. Now, there is a special case of extension of the hydrostatics when there is an additional acceleration acting on a body of fluid which isn't in the vertical direction from gravity. And there's basically two examples of this that we've got on the slide. The first one, the top one, a cart which has a reservoir of fluid which is constantly accelerating, right? So it has a constant force applied, and we assume that herein lies the big assumption. We assume that fluid inside the tank has enough time to reach an equilibrium state. So you've got first the cart, and then you've got the spinning case in the jug, in the second one, where it's being spun through an axis of rotation. Now, in both cases, but particularly the first one, when you apply a force, there's going to be an immediate impulse and an immediate kind of sloshing of the fluid in the tank. And this theory doesn't account for that sloshing. Okay, so when we look at the transient, the initial state that the fluid exhibits before it reaches an equilibrium, we can't use hydrostatics to analyze that. It's much more complex dynamics that are involved in that. But once it settles down, once it becomes like a banked fluid here, or with a parabolic surface here, then we can apply the hydrostatic theory. And we can do, because at that state, everything has kind of come to a rest. We assume that even though there is another acceleration applied, there's no relative motion between the particles. And to all extents and purposes, it is moving, or it is behaving like a solid body or a rigid body. So there isn't any particular relative motion between pockets of fluid in those cases. Okay, so first of all, we're going to look at how this slightly changes the equations of motion that we derived last week. And then we're going to look at how we get two slightly different sets of equations for these two slightly different scenarios. We'll go through, point out a few key points in each case, and then we'll have quite a few worked examples at the end. So along the top, you might remember that we introduced this expression last week, or at the end of the previous, where we said the sum of the forces acting on an element of fluid. So imagine you've got a big tank of water, and we're assuming a small element of fluid right in the center of that tank, which represents the state of the whole fluid. The sum of the forces is a pressure force, a gravity force, and a viscous force. And we use small f because that's the force per unit volume. That's the force per unit volume, and that's why we have density on the other side. So small f is equal to rho times acceleration. And we had these three terms that we derived: the gradient of the pressure, the weight, and the force due to viscosity. And we said that most of the time in a hydrostatic case, so in a hydrostatic case we're saying it's at rest, so this is 0, there's no viscous forces, and the only pressure gradient that's acting as a result of the gravity is in the vertical direction. So all we have is this, and so our three directions of the change of the pressure are defined uniquely by the situation. There's no change in x and y. The only change in pressure is due to the gravity in the vertical direction. And we summarize that with our specific weight, our gamma. Now, in contrast, what we're saying now is that when we have rigid body motion, we can have another acceleration. We can have another acceleration applied, but it's reaching still that steady state. So rather than this be entirely equal to 0, there is an overall force applied. There's an overall acceleration. And this is our rho, our mass per unit volume, times our acceleration. Both sides of the equation are per unit volume. You've got small f, force per unit volume, and here you've got mass per unit volume, density. It's a common way to treat these equations, per unit volume. You'll see that again and again. We still have gravity, so we still have the same change in pressure gradient in the vertical direction as we did in this case, but we also have a density. There should be a density there as well. We also have a change in the pressure gradient in the x direction due to the acceleration, ax. And it doesn't have to be ax, it could be ay, or indeed it could be az, right? So if it's az, then it will either enhance or counterbalance the acceleration due to gravity. Or, in a more realistic scenario, perhaps it could be a little bit in all three coordinate directions. And this is where the vector calculus comes in. And this is the extension that we're looking at today that allows us to consider slightly more complicated scenarios. So any questions on what we've introduced, what we're going to be looking at? Oh, all good? All good? Okay. So kick us off then. We've got this situation here, which I posted earlier. You've got this fuel tanker that is taking a liquid in a tank, an enclosed container, and you've got a similar problem where you've got an aircraft which is carrying a large quantity of fuel inside its compartments, and the question is, okay, these are both vehicles, they're both likely to move. What is the implication for the fluid inside them? What do we need to be worried about as engineers designing these vehicles? Anybody got any comments? The slushing effect, exactly. There's a couple of good answers on here already. I'm going to quickly post the other one while I'm here. So, the slushing effect. Now, why do we care about the slushing effect? Yeah.
Changes the center of gravity of the
the center of gravity, and it can change it quite drastically. The aerospace engineers amongst you, if you haven't already been introduced to it, you will be soon, that the center of gravity versus the center of pressure on an aircraft is a critical relationship. You need to know very precisely where your center of gravity is. On an aircraft, depending on the load that you're carrying, you have to change slightly the aerodynamic configuration. It's called trimming your aircraft. If you don't know the center of gravity, you can't trim it. Or if the center of gravity is changing, you have to trim constantly. What's the problem in the tanker, in the vehicle? Yeah. The inertia of the fluid. So what kind of maneuver might be a problem if you've got large quantities of fluid moving around? Turn, yeah. Yep, could all go to one side. I mean, basically anything, right? So braking is going to be a lot more dangerous because you're going to have this large shift of center of gravity as you brake suddenly. And so this is a big problem. This is a big problem. Some of my colleagues in the department have been working with Formula One teams, trying to understand ways to control how the fuel tanks distribute their mass during the race. Because, like you said, cornering, it hugely influences the very fine margins that performance that a car like that is designed for. So what can you do about it? What's the solution? Yep, that's one thing. So baffles. You can introduce basically plates that have orifices inside them so that they only allow transfer of fluid at certain points. What else can you do? Yep. Sorry? Can you make it stationary within the container? Sorry, say that again. I think I missed. Okay, so can you control the dynamics of the fluid when you're braking, I guess, or move it to one side, maybe? Or... So I think what you're getting at is pumping. So you can pump the fuel around the container. So aircraft do this quite a lot. When you are partway through your flight and certain levels of consumption of your fuel, you redistribute constantly the fuel around the aircraft to always maintain a certain center of gravity.
So we just delete entirely the fluid so that it will not have any space to...
Yeah, you could, but then when you use the fuel, it will decrease. Right? Yes, but as soon as you change your maneuver, that might be okay in a plane, for instance, because you're generally may not be moving a lot, but in a Formula One vehicle where you repeat the same maneuver 60 times, it'd be a problem, yeah. Sorry, say that again? The dihedral angle. Yes, we're getting into aircraft stability and control now, but yeah, absolutely, a dihedral angle, so that's when your wings kind of go up, looking head on, can kind of counterbalance some of the effects. Yeah, it's like unconditionally stable. So if it moves to one side, it rolls it back to the equilibrium. Yeah, but that's a different matter. So basically, we've got this quite large mass. Remember, fuels in an aircraft can be a significant proportion of the mass in it, right? In a space rocket, you're talking about maybe 90+% of the mass of the vehicle on the launch pad is fuel. I mean, that's a special case, and in a space rocket, you're not doing a lot of complicated maneuvers. But when you have a lot of fuel, you have to work out how to control it when it's being maneuvered. And this is a classic problem with fluids. And in certain situations, you can refer to it as a rigid body motion. So you have a tanker at rest. The only acceleration acting on the fluid in the tank is gravity. And then as soon as it's accelerated, there's an equal and opposite force from the tanker on the fluid and the fluid on the tanker. So the fluid basically migrates to the back of the tanker, and you have a resultant. And that resultant is no longer vertical. It has a horizontal component as well. So we now need to reconsider the alignment of our fluid. And this is basically where the theory of hydrostatics comes in. Pressure gradient effectively has changed direction. When the fluid's at rest, the only pressure gradient we care about is vertically down. The pressure gradient is increasing as a function of the distance from the surface due to the amount of the weight of the fluid above it. In this scenario, not only do you have the weight of the fluid above it, you have the force applied to the side as well. This is the general case taken from the textbook. Looks a little bit more complicated, but the difference here is instead of just having a horizontal force, this is the general case where we're introducing also a vertical component to the force. So now this vat of fluid is not just being accelerated horizontally, it's being accelerated also with a positive AZ, which is counteracting the gravity. And then you have to, this is where you start to have to use vectors in order to analyze the sum of the two accelerations. So you've got gravity and you've got this minus A, and you get this, basically this vector, and you can then decompose the components of A and Z to calculate the effect on the fluid. Yes?
In practical examples we've trained as well, you see something about AZ. How do we find the other vertical acceleration other than gravity?
So in this example, it would be given, right? So this is an example where perhaps the previous one is practical. We can understand that. It would be a vehicle that's moving on a road. This example, it might be a vehicle that is being carried by another mechanism or transported in a plane. So it's just more general in the sense that it has a component that's not just in X, it's in Z as well. So that's the only difference. And what happens is it effectively adjusts the free surface. So whereas previously our pressure gradient was purely gravity, now it's the difference of the two vectors. Gravity is down, and A is generally positive up. Remember that Z, X, Y, we assume they're positive directions in a standard coordinate system, and gravity is always negative of the Z. That's why you have G and A. Yeah.
I don't really understand the adjusted free surface. Is it like, so you know how it shows horizontal free surface? That's what actually is.
Yeah, so I'll show this in the next slide in a bit more clearly, but the horizontal free surface is what it is before the acceleration is applied. Yeah, so it's not very clear here. So before the acceleration is applied, you have the horizontal free surface. When it's applied, it tilts. Continuity? Container. No, this is a more general example of the same situation. So in the previous one, you had an acceleration purely in the X direction. In this one, you have X and Z, so it's going that way. And this is just to show you that the force that is applied doesn't have to be in one coordinate direction. It can be in any arbitrary direction. And the two things that you have to work out when you're addressing a problem like this is the angle, the new angle to the horizontal, and, if you like, the new direction of the resultant. The new direction of maximum pressure gradient, like the new, if you like, the artificial depth. And this is what we illustrate here. So as was pointed out before, this is just showing the initial state. When you accelerate it, it banks. All the fluid goes up on the opposite direction, and we have effective change of pressure in the same direction as the free surface. So the yellow lines are what's called iso lines, isobars. They denote parts of the flow that have constant pressure. So the free surface has the same pressure, it's atmospheric. And then each one of these lines has a progressively higher pressure as you go deeper. And the pink arrows denote the direction of maximum increasing pressure. And because it's a linear acceleration, then all of those lines are parallel. And that's, if you like, our new situation. Once it's reached that state, we can apply the hydrostatics exactly the same way that we've done in the past. Okay, there's a few examples of that coming up in the next section, but first we're going to quickly look at the case for rigid body motion as well, rigid body rotation. Okay, so this example, you've got a magnetic stirrer. So basically what's happening is underneath the surface, there's a beaker of water that's put on a surface, and there's a magnet that's spinning round that's attracted to the stirrer that's inside the fluid, and it's a very effective way of stirring a fluid without having to connect it to an invasive apparatus. So you can basically, once you finish stirring, you just need to take the stirrer out. A commonly used process in manufacturing. And what you see is the free surface forms this kind of parabolic dip down, which eventually touches the surface, the stirrer. And you can see that while it's never actually stationary, the general shape of the fluid surface is more or less constant. It's always shaking. It takes a while to reach the point where it touches the bottom. But once it does so, we can assume that it is in a rigid body rotation state. Once we know that state has been reached, we can evaluate the distribution of pressures in the fluid using the same approach. And this has applications to a range of different configurations, particularly pumps and fans, that we use this for in fluid dynamics and in engineering. And basically what we're saying is that once it reaches that state, every point of the fluid in that tank, whether it's on the center line or out to the side, has the same forces acting on it. It has a force due to gravity and a force due to circular motion. And that force is no stranger to you. It's essentially mv squared over r. It's your centrifugal or centripetal force, depending on your perspective, which you will have come across in circular motion. And now it's applied with respect to the central axis of rotation. And it's the combination of that force, the gravity force, and the circular acceleration, which now defines the new direction of isobars and the direction of depth, if you like, the direction of effective depth. And this is illustrated here by this experiment. Well, the photos are taken from the Frank White textbook. And here you have a mixer, so a cylindrical mixer, which is first on the left at rest, and then on the right it's being rotated by an angular velocity omega. And it has streamers, buoyant streamers. So these are basically pieces of string which float, try and reach the surface. When it's at rest, these streamers float vertically. When you accelerate it with a circular motion, they kind of collapse inwards. And this is representing the direction of the effective depth, the resultant force that's acting on this fluid. Similar to what we had in the last example, your yellow lines are representing pressure iso lines. So everything along those lines has a constant pressure. It's a bit crudely drawn, but basically the free surface is always at a constant, and if it's open to the atmosphere, it must be atmospheric pressure. And then you can see that the variation of pressure is different according to where you are in the tank. If you're at the center, then it reaches a lower pressure sooner. And you have, again, the pink lines representing the lines of effective depth, maximum increasing pressure. And you can see that they're no longer parallel, they're flaring out towards the corners. They're effectively always orthogonal to the individual pressure iso lines. Okay, so I think we just do one more kind of theory slide, and then we put this into practice and go through a few examples. So in a very similar way to what we introduced in the rigid body motion, we changed the acceleration. This time, previously, we had gravity as our acceleration and AX. This time we have gravity and we have half mv squared, or half r omega squared. Sorry, half mv squared, yeah. So this is effectively the same thing in terms of omega, and it's representing the acceleration due to circular motion. And this expression is telling us basically that the sum of these two pressure gradients result in the overall change of the pressure. So there is a pressure change due to the change in Z and a pressure change due to the change in R. So versus this axis, if you go this way, in the radial direction, you're going to increase this term. R is going to be non-zero because at the axis R is 0. And depending on your angular velocity, this will increase. And as you can imagine, as you increase the angular velocity, there's going to be a greater force to the sides of the tank. So the pressure is going to increase in the direction of the radius. That's why it's positive. dP over dr has an increase in the same direction as r. So the farther you go away, the greater the pressure is going to be increasing. And our gravity is the same as it always is. As you go deeper, it increases. That's why it's negative, because Z is defined up and gravity goes down. Okay. So, a few new concepts. Now we start to put them into practice. Okay, here's one for a bit of a discussion. You have a train leaving a station at a constant acceleration, and a balloon is released in the center of that train, and there's no other obstacles, and the balloon is free to move. The train continues in a constant acceleration, and we assume that the air inside it is under rigid body motion. So what happens to the balloon? The balloon goes backwards, the train goes forwards. How come? It feels intuitive to say that, but it's not actually the case. Yeah, up there. Sorry? No, we can just assume that it's air. So it's air and it's in air. Yep. Okay, the answer here is that it stays in the same place because it's in the same reference frame. Okay. Interesting. Any advances on that? Yep, the front.
Since there's no relative motion between particles in the fluid, they're not going to move relative to the train either. So they're going to stay. The balloon, since that's basically just air as well, will stay in the same position relative to the rest of the train.
Okay, so a reinforcement of the second answer, that since there's no relative motion between the air particles, the balloon, which is itself encapsulating air, will stay in the same place. Okay, neither of these answers are correct yet. They're good, but they're not right yet.
Since the balloon has mass, wouldn't it flow backwards?
Okay, yeah, so the resultant force on the balloon, there may be a transmission of the acceleration through the air to the balloon, so there might be a resistance or a tendency for the balloon to go backwards. But what have we just been talking about? Yeah. It'll move forwards. Right.
Because when the train is moving, all the air will go to the back and there is a low pressure in the front.
Exactly, exactly. It's counterintuitive. If you release a balloon in a train while it's accelerating, the balloon, very much counter to what you might expect, will float to the front and to the top of the train. And this is because the acceleration applied on the air causes a rigid body motion and a pressure gradient to form to the back bottom corner of the train. So this means all the air goes to the bottom due to gravity and due to the effect of the acceleration. And so there's a stratification of the pressure to the top front corner. That pressure gradient causes an imbalance of forces which probably overcomes the response of the balloon due to its mass and causes it to float to the top corner. So that's a bit counterintuitive. It takes a bit to think it through. So let's kind of break it down into different steps. Okay. So the first part of the explanation is to identify how the pressure varies. So we have this situation where we have our train at rest, and then we have it accelerating in a positive x direction. So we've got our two components of acceleration. We've got our AZ and our AX. Whether it's at rest or accelerating, the vertical component is the same. That's the first key. The vertical component due to gravity doesn't change. What changes is the horizontal component. If it's at rest, there's no acceleration in the x direction. So according to this formula here, if AX is 0, the PX is going to be, dPdx is going to be 0 as well. If AX is positive, as is the case here, which is actually the case that we're looking at, then dPdx is going to be negative, right? Because it has a negative in front of it. So the pressure is going to reduce in the x direction. And in the case where it's decelerating, the opposite is going to happen. Pressure gradient is going to be positive, because if the AX is negative, dPdx is negative, sorry, it's positive. So you get an increase in the pressure direction. And what happens is represented by this gradient here, is the pressure backs up to the back and to the bottom. Yep. Where the highest pressure is in the bottom back corner. Here. And the lowest pressure here. Yes?
Sir, the balloon will move forward due to this pressure gradient. Because the pressure of the air, because the pressure is higher backwards than forward, the air will push the balloon forward, and that's how it works.
Exactly, exactly. And this is what's represented here. We have a zoom picture of the air inside the train. We've got our high pressure on one side, our low pressure on the other side. Pressure is a force per unit area. The balloon is the same regardless of the side that you look at it from. So the net force is going to be going in the vertical up and forwards direction. It's going to move from the region of high pressure, which put another way is high force per unit area, to the region of low pressure or low force per unit area. Yeah. How? Yeah, very much so. I mean, winds, do you mean in terms of the response of buoyant objects or objects that can be blown by the wind, or you mean how the atmosphere is? Yeah, we won't get into that, but effectively, the atmosphere is always playing a game of moving into voids of low and high pressure. So where there is a region of low pressure, it pulls a system into it, right? So it's a bit more complicated because you have changing densities and temperatures, and you have a vertical effect as well. But the principle is exactly the same. High pressure to low pressure. Okay, good. Okay, so a couple of special cases to consider. When we look at the case where a tank is being sloshed, we have to, unless there's been a spill, we have to consider conservation of volume. If there's a spill, if we lose some of the volume, it gets harder. Unless we know how much of the volume of the tank has been lost, it's going to be hard for us to solve the problem. In this example, we're saying that a tank has a non-zero acceleration applied to it, and there's no spillage, so we can say that the volume at the top must be the same as the volume here. So the old volume, B times H per unit width, we're just assuming the width is 1, it's got to be the same as this rectangle plus this triangle. So we define this dashed line as the original line, which is height h from the base. And we define this new h, which is the difference that it's risen on one side and fallen on the other. And we get this rectangle and the triangle. And those volumes, or areas at the moment, have to be constant. And if we equate that, then we get an expression for the angle, which we can equate to the expression for the acceleration. Remember, the resultant at the acceleration is tan to the minus 1 x over gravity. And if we equate those angles, we get an expression which directly links the maximum acceleration that the cart can go before there is a spill. Okay, it otherwise looks like quite a complex dynamic problem. What is the maximum acceleration that you can have for a given container before it starts to spill? But it boils down to a very simple expression. Yeah?
Over here, for a new volume, you see B over 2 to H2. Can this be simplified to
BH2.
Oh, a new volume.
Up. On the next slide.
No, this variance is
Oh, this one here.
No, I'm not talking about this. The original volume is equal to new volume. On the left side.
Yeah, okay. BH minus H2. Yeah, so we don't know. So the question is, what does 2 times H2?
It's B over 2 times 2H2.
Yeah.
Simplified to BH2.
Sorry, say that again. I couldn't hear you.
There's B over 2 here.
Yep.
There's 2H2 multiplied with that. After 2's cancel out.
Capital H. So this guys, quiet down while I try and answer this. Thank you. So all we have here is we have a general situation where the tank has risen on one side and fallen on the other side. And it might look like H2 is half of H, but it might not always be. Okay? So what we have is a deviation from the original up and a deviation from the original down on the other side. So what we have is the rectangle at the bottom, and then we have half base times height, which is B, times 2h, which is the height of the triangle, times half. So if it is the special case where 2h2 is equal to h, then you can simplify it, but it's not generally that. It's a general expression. And this is tested in this example, which I think was part of an exam question a few years ago, which basically, if you're given this expression, how can you calculate the maximum acceleration which is applied? It's as simple as plugging in the numbers. If you know the base and you know the maximum height that it can reach, then you can solve the problem. So I want to show you a slightly more complicated problem before we, a couple of problems before we finish, actually. Okay, so this is one that's been inspired by the application I mentioned before of a tank which is subject to an acceleration. And the tank is parameterized, so it has a height h and a base 2h. And we're asked to find out the acceleration of the car when in the special case where the free surface just touches the bottom corner. Okay, so it's a geometric consideration. We have this, we know what the height of the liquid is. It's filled up to a third of its height. And we know then what the size of what the triangle looks like after it's met, the free surface has met the bottom corner. So we apply the conservation of volume rule. So to start with, we have 2h times h over 3. That's our rectangle. And here, we must equate it to half base times height. So half of h nu times 2h. And we can solve that to show that the link between h nu and h is that it has to be 2/3. of the height. Once we have the new height, then we can equate this using the expression that we had on the previous page directly to the acceleration that must apply in order to result in that condition. So the tans cancel, and we're left with AX is equal to GH nu over 2H, which gives us 3.27 meters per second squared. Again, this is a significant assumption because we're assuming that it has time to reach this state. But at the same time, this is a back-of-the-envelope calculation that you can use as an engineer in this domain to get an order of magnitude to find out what problems that you might encounter with a fuel tank design. So it's kind of already becoming something that, that is being used in an applied way. Okay. Still got a few minutes left, and I just want to cover the last few slides for you. So there's a special case now where we consider the rotating tank, and we consider the situation that this parabola has just touched the base of the tank in the center. So we look at the special case. We're asked to find this particular case where at the side it raises a height of ZC, and at the center, the free surface just meets the center. So we have 0 height at the beginning. So the change in height is from ZC to 0. So it's ZC minus 0 is ZC. And the change in the radial direction is RC at this point at C minus R at the center, which is 0. So it's RC squared. And this gives us the total combined pressure change between the center and the height C. If we assume that those two pressures are the same, or because in the steady state situation where it is effectively static, that free surface is constant, and any point on a free surface has the same pressure, so they cancel. Then we can reorganize this to get a similar relation to what we had in the rigid body case between angular velocity and the dimensions of the container. These are two examples of how you can manipulate these sets of equations to solve practical problems. And in this, the extension of this problem is exactly the same information, except we plug numbers in this time. This time you're asked that a cylindrical container has 15 centimeters diameter, and the height at the sides of the container reach 30 centimeters. So with that information and the expression that we've derived from the previous slide, we can calculate the angular velocity that's needed to produce that free surface. Now, so in an exam, you're going to be given the equations and you're going to be walked through the analysis needed to get to that point. But again, it's really important that you know what to do with the equations if you're given them. And so this is kind of an example of where you have to know how to interpret the equations for a given problem. I think actually there's a tutorial question a bit similar to this coming up. If not this week, then in the next one. Okay. The last thing I want to point out is there's another practice question. This is a worked solution from the textbook. This is something that I'd recommend that you try and do. And tomorrow I'm going to post a video solution for this. So if you don't have time to do it before then, feel free to watch that and follow that through, and it should explain. Okay, that's it. I'll see you Thursday. Some of you tomorrow.
It's always going to be that, right? So surface is always going to... So the height, the rectangle height effect, and the height will always have its line across the original. Yeah.